Okay, so today we'll kick things off with a recap because we're moving into a new area, which is phase equilibrium, so multi-phase single component right now. So I'd like to do a quick recap of how we got to here, and then we'll expand on it and how we actually can use an equation of state to calculate vapor-liquid equilibrium. So, a quick first recap. So the very first thing that we talked about was the first law of thermodynamics. Right, and this is essentially just an energy balance. So in this case, we had du is equal to delta Q plus delta W. So any energy that enters a system or leaves a system in the form of heat or work, we can tally that up, that the system has to somehow store that energy. And the way that it stores it, we just call it internal energy. Right, and this is back in the day when we didn't know really how the matter was storing the energy. Some matter could store more, some matter could store less. We're just saying it's in there somehow. The second law, what am I doing? Sounds like I need a weekend. Okay, the second law can be written simply as ds is greater than or equal to 0, and that d squared s is less than 0. So effectively, the second law in its most basic fundamental form only says this magical term called entropy always increases until we hit equilibrium, and then it's constant. And we were able to use a relationship between the first and second law to basically say that the entropy should be related to Q over T, basically, right? The rate of entropy coming into the system. 3, we defined some new variables. Namely, A is defined as U minus TS, G is defined as H minus TS, and H is defined as U plus PV. These are just convenience units. And soon, maybe today, but most likely on Monday, we're going to add this F variable. Who remembers what F stands for in thermo? Fugacity. So fugacity is just another conveniently defined variable. But ultimately, everything that we're doing when it comes to phase equilibrium, multi-component phase equilibrium, chemical equilibrium in terms of reacting systems, it all goes back down to just the first and second law of thermodynamics. Everything that we're doing is just adding complexity and to some extent arbitrariness to those first two laws. And that's why I always state that we're teaching really the system and the convention, because we're just building on it and building on it and building on it, and we're manipulating those equations in order to get to some form that's more useful. Because we don't have an equation that can measure energy, we don't have an equation that can measure entropy. We have to find a way to relate those to temperature, pressure, and volume, things that we can measure. And so it just so happens that a unit like fugacity is really convenient for calculating phase equilibrium, more so than the Gibbs free energy. Right? Because again, the Gibbs free energy is this really abstract concept as well. So if we're already working with an abstract concept, let's just use one that's easier to calculate. So the next step is we use the first and second law plus the Gibbs phase rule right? Basically, the Gibbs phase rule is on the basis that U, S, and V are the main variables of sort of the universe in a thermodynamic perspective. So if we know any two of them, we should be able to calculate the third. So any thermodynamic variable that we expand using calculus has to be with respect to two other variables. And so from there, we were able to translate U and S into units of T, V, and P that we could measure or calculate using an equation of state. But all we did in that section was just general multivariable calculus. So if I wanted to know, let's say for example, how much the internal energy changed of a system, I would have to expand it as a function of two other variables, right? How do things change as a function of dx and as a function of dy? This is general calculus. No sort of thermodynamic component to it at all. Okay. The next step we did is we used the equilibrium criteria that ds is equal to 0 and it's at a maximum at equilibrium. And we constructed a system, as we do with many of the other systems, where we had chamber 1 and chamber 2. And this is the total surrounding system is an NVU. N meaning it is a closed system, no masses entering or leaving. V meaning the total volume of the system is constant. So there's no PV work that can sort of go in or out of the system. And U, coupled with the constant volume, tells us that there's no heat going in or out of the system. So from this, we developed three equilibrium relationships. We had mechanical equilibrium, in which case the pressure of chamber 1 had to be equal to the pressure of chamber 2. Right? For example, chamber 1 could be a liquid, chamber 2 could be a vapor, it could be two solid phases, it could be two liquid phases. We had thermal equilibrium, where temperature 1 is equal to temperature 2. And we had chemical equilibrium, where the Gibbs of phase 1 had to be equal to the Gibbs of phase 2. So we're adding a lot of complexity, but you always have to remind yourself and convince yourself that this is all just clever manipulation of the first and second law based on these sort of arbitrarily constructed systems. And from there we went a little bit further and then said add a constant PT system, or we could write this also as an NPT system, that the Gibbs free energy is equal to a minimum. So dg is equal to 0 and d squared g is greater than 0. So that the Gibbs looks like this. G as a function of basically any other variable there. And this is really the basis of what we're going to use for a lot of the phase equilibrium calculations that we are concerned about. Because for us, it's much easier to have a constant pressure system than it is a constant volume system, but that's not always necessarily the case. For us, it's just easier to control pressure with respect to a pump or a valve or something like that. We use the stability criteria of entropy to show, well, we didn't really show it, but we talked about how one might show it, to show that the heat capacity is always greater than 0, meaning that if you put energy into a system, its temperature has to go up, and a relationship between P and V that always has to be less than 0, so that is, that's not the concavity. So the slope of this expression on a PV plot, right, you always have to look something like this where you have a negative slope. And this is what we're going to be talking about today to a large extent. And then lastly, if you combine everything, the first, the second, and the third law, we basically show that T always has to be greater than 0. You can never actually thermodynamically reach absolute 0. Not something we're going to talk about too much, but interesting to know nonetheless. Okay. So again, everything we're doing is just building on the last section, adding complexity, modifying the system, adding phases, adding multi-components, and we're just manipulating the frameworks that we have established previously. But given enough time, right, we should be able to, from ground zero, rederive everything that we're talking about today from just du is equal to delta q plus delta w, and ds is greater than or equal to 0. Everything we're doing, we could start from there, but instead we're just kind of skipping along the way. Okay, so now we're going to lead into talking about a cubic equation of state. And often I will write this as EOS. So before we build up to a cubic equation of state, let's explore some other equations of state that we kind of march up in terms of the complexity. So the simplest equation of state that we have is just the ideal gas law, in which case I generally like to write it PV is equal to RT. And for a closed system, this is a really easy way to write it. A lot of the times you'll see P is equal to rho RT, or in StatMech you'll maybe see PV equal to rho KBT. So in this case, this would be molar density. How many moles per unit volume are there? In this case, this would be a number density. How many particles or molecules are there per unit volume? And just as a recap, we won't really talk about this too much, but R is equal to NaKB. So if you ever find yourself in a StatMech calculation and you can't remember what the Boltzmann constant is, because I certainly never can, I can remember what R is, and I can remember what the Avogadro's constant is, and you can always calculate Kb that way. So that's how they're related. So the ideal gas law is always stable. So dP dV at constant t, and we showed this in class, minus RT over V squared. This is always less than 0. So the ideal gas is always stable. So if we show a PV plot here, it looks like a radical curve, and no matter what, you have a negative slope no matter what the PV conditions you choose are. Always stable. But for any particular pressure, so if I call this P1 and I call this T1, for any point in space of pressure and temperature, right, this is the intersection here, the ideal gas law will only ever predict one phase. I choose a pressure, I choose a temperature, here is the volume, no matter what. And that phase that it predicts is always stable, no matter what. So essentially, what this tells us is that the ideal gas law thinks that everything's a gas. It thinks a solid's a gas. It thinks a liquid's a gas. It thinks a gas a gas. Everything is a gas. There isn't any other phase that is predicted with the ideal gas law. So we'll step it up, and we'll talk about the virial equation of state. The virial equation of state can be written as PV over RT. This is equal to Z, the compressibility factor. So oftentimes Z is a really convenient unit to use. And we can write the virial equation of state as equal to 1 plus, 1 plus B as a function of T over V. So if, for example, the virial coefficient, if B of T is equal to 0, then Z is equal to 1, which basically means that we have an ideal gas. Or if V approaches infinity, again, Z is equal to 1, we have an ideal gas. So what the virial coefficient takes into account is as your specific volume goes down or your density goes up, you'll start to have some intermolecule interactions. And those interactions are characterized in the virial coefficient, which is a function of temperature. This is something that we can derive from statistical mechanics. But as your density goes very, very low, those molecules don't feel each other anymore, so the system should begin to behave like an ideal gas again. So the limiting cases are totally okay. So if we rearrange the virial equation of state, we can get that P over RT is equal to 1 over V plus B over T V squared. And eventually we can write this as and this is a quadratic formula. So if we were to plot this function, it should look something like this. So I'll call this T1 because we're drawing an isotherm. We're following along a path of constant temperature to see how the pressure and volume relate to one another. Then if I draw a second line at constant pressure, we see that we have two phases, phase 1 and phase 2. So the virial coefficient will predict that multiple phases exists. However, there's a problem. In this region, dP dV is less than 0. We have stable phase. And this region over here, dP dV is greater than 0. Unstable. This phase just physically cannot exist. Because any small perturbation, any small fluctuation in how one molecule is arranged compared to another will increase its entropy when you're in the unstable region, which means that it can never form. So the virial coefficient, or virial equation of state, is also insufficient to do multi-component phase equilibrium, because it only predicts one stable phase. Now let's talk about cubic equations of state. And so we're going to start off with the simplest one, and this is basically the only equation that I'll ask you to manipulate in any real capacity, because the other ones are extremely tedious to manipulate. You may have to code them up and program them, but I won't necessarily ask you to analytically manipulate them other than the van der Waals. So the van der Waals equation of state is not particularly accurate, but everyone likes to use it because it is the simplest. Now the equation is P is equal to RT, V minus B minus A over V squared. Who's seen the Virial equation of state? I'm sorry, the van der Waals equation of state before? Hopefully everyone. So what is B? How could I physically describe what B stands for? Yes?
It's supposed to represent the volume that's actually taken up by a molecule of gas.
Exactly. It's the excluded volume. And what units should B have? Yep, specific volume units. So it should be meters cubed per mole. So remember, in sort of dimensional homogeneity, or basically consistency of units, if I'm adding and subtracting things here, they have to have the same units. In multiply and divide, anything goes. But in add and subtract, you have to add 2 units that have to be the same. So I can't add 12 feet to 12 inches, right? Because obviously that doesn't make any sense. It's not 24 feet inches. Okay. What is A? What does A characterize? Yes?
Pressure exerts on the wall by the molecule.
From a molecular perspective, what does it characterize there?
Interaction, right?
It's the interaction of molecules. Okay, what units should A have?
Mole squared per meter 6, per meter to 6.
Almost. Which units does, so let's break it down. This term here, what units does it have to have?
Pressure per mole square. Pressure by mole square.
Almost. Almost.
Meters.
All the pieces of the puzzle are there.
Meters to 6 divided by moles to the squared, I mean, it's
Almost again. We're missing one thing.
Kelvin.
So let's step back. So this term here has to have, when I'm done multiplying all this A and V squared, what units does this term have to have? It has to have pascals. This is a pascal. This is a pascal. So that means A units has to be meters to the 6th moles squared per times by Pascal. If I did my math right. Because V squared will, so V has units of meters cubed per mole, square that, meters 6 per mole squared. That has to cancel out with the A, and then A also has to deliver units of pressure. Okay. Now, next step. If A is greater than 0, is this attraction between molecules or repulsion between molecules?
traction. Because then we're going to lower the pressure, so they're going to have to attract.
Bingo. So this is attraction. So it lowers the pressure. Right? If A is positive, that means that this term is pulling down the pressure that is being exerted against the wall. So conversely, if A is less than 0, this is repulsion, where pressure goes up. So, under what circumstances do we expect molecules to be predominantly repulsive, let's say? Tell me a configuration of molecules in a system where we would expect that they would want to push away from one another.
Two highly electronegative molecules, I guess.
Well, but as a bulk fluid, there has to be neutral electronegativity. So if you have an ionic system like a sodium and chloride, and we're talking about bulk sort of thermal calculations here, you have to have a net balance of positive and negative charge. So you can't ever have a net difference of charge. So I'll pose it a different way. Would we expect molecules to be attractive or repulsive? So which of the two situations? At high density, is it attractive or repulsive? Or at low density, is it attractive or repulsive?
At high density is attractive.
At high density, it is extremely high density, I should say.
Repulsive.
It's repulsive under those circumstances. And at low densities, they're always going to be attractive. And so a lot of times, especially in molecular simulations, and this is really always an interesting way to think about molecules. Let me redraw this actually. You can have a net force acting on a particle as a function of distance. Now, the most commonly used intermolecular potential that determines whether things are attractive or repulsive that people use in simulations is what they call a Leonard-Jones 612 potential. And it looks something like this. So at far separation distances, I should write, the nomenclature typically uses R here. At far separation distances, things tend to be attractive to one another, and the molecules want to stick together. Now, the reasoning behind that has to do with van der Waals interaction forces. So this part right here is attractive on the order of 1 over minus 1 over r to the 6th. This is where we get the name 612 Leonard-Jones potential. Right? So the molecules want to attract to one another. And this is a theoretical prediction that you can show, is that the attractiveness follows this, 1 over r to the 6th power. So how this actually physically works is when you have two molecules that are identical, the electrons in that molecule are going to be sloshing around at some sort of a frequency. And that frequency is going to be very specific to the chemical bonding, the chemical composition. And that frequency will have very slight domains of positive and very slight domains of negative. And those will all get in sync for a single pure component system. Now, if you perturb that in any way, change the bonding a little bit, change the composition a little bit, that sloshing of the electrons will be very slightly different. And that's why two dissimilar molecules will never have exactly the same attractive reactions as two of the same molecule. Now, the reason here for this really steep going up is because we have overlap of the electron clouds, and they're repulsive. So a lot of times you'll ask, okay, so why is it the 612 Leonard-Jones potential? Because 12 is just taking 6 to the power of 2. So computationally, it's very efficient to calculate. So if you're doing these types of calculations and simulations in a computer, you want to be able to do millions of molecules for very long time periods. So you need to cut down every single step along the way for calculations. And we'll go more into this in the second half of the class when we talk about StatMech. But this is really the molecular underpinnings of non-ideality, is how do individual molecules interact. So what we're talking about now, we don't have any idea about this, right? So we have to forget about this when we're thinking about the math and the nomenclature and terminology of classical thermo. But when we transition into StatMech, the whole goal of StatMech is, can I take a simple model, relatively simple model like this, and say, okay, I'm going to build a game. And I'm going to say that two molecules interact following these rules. And then I'm going to put 1 million of them in a box, and I'm going to see how they behave. That is exactly what modern thermodynamics is like. And so instead of talking about PV relationships, we're talking about what is the best way to model this particular interaction between, let's say, a water molecule and a lipid, or a lipid and something else, or a solid suspended in, a fluid. Right? So we've simplified the problem down to talk about the core fundamental physics of the process. But for classical thermo, no, we have no idea about any of this. Okay. So if we rearrange the cubic equation of state, we can get a form that looks like this. P V cubed and so clearly this is a cubic function. So oftentimes, and especially in the Sandler book, when you're talking about different cubic equations of state, you'll often write your own personal code to be very generalizable. So AspenTech, for example, or any other fluid flow or fluid phase simulator, they're not going to code up, an entire system for the van der Waals equation, and then for the Peng-Robinson equation, then for the SRK, and then for whatever equation of state you're going to use. What they're going to do is they're going to generalize it into a form like this, where we have our variables here, and then we have some coefficients. So we could call this A, call this B, we could call this C, we could call this D. They're going to generalize it so that if I want to switch from the van der Waals equation of state to the Peng-Robinson equation of state, I don't have to recode everything. I just recalculate A, B, C, and D differently. as a function of temperature or whatever other parameters are necessary. So the generalizable form of a cubic equation of state is really useful. So if we are to draw out then the cubic equation of state, it should look something like this, and in the homework that I will be assigning shortly, it kind of looks a bit like this. So we have pressure and volume. Again, specific volume, so another way you can think of it is density. It's the reciprocal of density. For any given pressure, I'll call this P1, and this line that I drew is an isotherm. Because if I look at the cubic equation of state on the top here, I have to specify the temperature at which I want to relate pressure and volume. Because remember, everything's a function of everything in thermodynamics. So if I want to evaluate this expression here, I have to only have two variables. One dependent, in this case that's the dependent is pressure, and then the independent variable is volume. So I have to fix the temperature if I want to evaluate this equation. So that's why we use these isotherms. So this is a path of constant temperature. So at the intersection of the pressure and the temperature, we have these solutions to the equation. Right? This is how we used to solve multiple systems back in, 8th or 9th grade in your geometry or algebra 2 class. You would draw one line, draw the other, and when they cross, boom, that's your solution. So here we have three roots to this cubic equation. This corresponds to three volumes. We can call this volume 1, volume 2, and volume 3.
Doesn't the second line not matter?
Correct. So only two of these are stable phases. And it was already pointed out that volume 2 is unstable. Doesn't count. It's not a real fluid. So if we were to draw out these regions here, in this region on the far left, dP dV is less than 0. We have a negative slope, stable. In this region here, dP dV is greater than 0. This is unstable. And then over here again, dP dV is less than 0, so we have stable. So the cubic equation of state is the physically simplest mathematical expression that we can use to have two stable phases. Is there some fundamental rule of the universe that tells us we have to use a cubic equation of state to do multi-component or multi-phase equilibrium? The answer is no. There is no reason other than it is the simplest way that we can contain the physics of a vapor-liquid phase transition on paper with math. Now, the way that we had come up with the form of the cubic equation of state is based on fairly sound logic, right? As we increase the density, we are going to be having molecules that occupy a greater fraction of the volume. That's the excluded volume, that's the B. The A term is the interaction of the molecules. Again, we should expect that to be a function of the density as well. So the formulation of the cubic equation of state is just sort of a mathematical convenience. There is no fundamental rule of the universe that says we have to use an equation in the form of the van der Waals equation. It just, the system that we decided works pretty well. So, now that we have a cubic equation of state that shows us vapors and liquids coexisting together. Now we'll do one last quick question. Which one is the vapor and which one is the liquid? So V1, what is this, the vapor or liquid?
Liquid.
That's the liquid. Can someone tell me why?
Lower volume.
Bingo. Much lower volume. Low volume, high density. So then, of course, V3, that is the vapor. Okay, how do we use this to solve practical problems? So what I drew there, in this case here, I'll draw a little small schematic up here. This is T1. In this case, T1 is less than the critical temperature. Above the critical temperature, the system should break down and we shouldn't see this wobbly effect. Because above the critical temperature, there should only be a single phase. So what we showed earlier is that for a constant PT system, the Gibbs is at a minimum, at a phase equilibrium. So in other words, dg is equal to 0. All right, so if you got another little quick plot here, g is a function of whatever. The slope, when g is at that minimum, is 0. It's flat. So this expression that I'm going to write, dg is equal to, v dp minus s dt. This is just a way that we have reorganized the first and second laws of thermodynamics. So if you go back to that table that I handed out maybe 2 weeks ago, this is just one of the expressions that's on there. We derived this maybe 2 weeks ago, so we're just going to rely on it, that we trust that it's valid. So all of these equations here relating between G, P, T, S, H, V, U, whatever they are, these are all just manipulations of the first and second law using calculus to transform out of one variable and transform it into some other variables. And the reason why we can do the transformation from one variable to the other is because we're assuming that there's only 3 variables we have to care about. And that limits how many transformations are available to do. So what we're going to do is we're going to say we're going to follow along a path of constant temperature. Right? That's our isotherm that we're following along. So then, if we integrate, or we follow along a path, so dg is equal to v dp. So if we want to go from a liquid to a vapor, we'll write delta G is equal to G of the vapor minus G of the liquid, which is equal to 0, because the Gibbs free energy is constant across the phase transition. So if these two phases are in equilibrium with one another, the Gibbs have to be equal to 0. And that this is equal to the integral going from a liquid to a vapor of V dP. So all we're doing is using a simplified form of the first and second law. Okay, so how do we actually evaluate this expression? So I'm going to draw a very large schematic here. P and V. This point right here, I'm going to call PB. This point here, PA. And then I'm going to draw some value in the middle, which I didn't actually do a very good job, and you'll see why I didn't do a good job in a moment. I'll call that P alpha. So what we're trying to evaluate is the integral of from liquid to vapor of V dP. Now this is a little bit different than what we're used to in normal calculus, because normally we integrate with respect to the x variable on our plot. In this case, we're integrating with respect to our y variable. So it's going to be a little bit sideways, but I think it's useful to show the work. Okay. So what we have as our basis is that 0 is equal to GV minus GL, which is equal to the integral from liquid to vapor of V dP. So this pressure alpha is our guess of what we think the vapor pressure of the system is. Right, because if we know the vapor pressure, we can calculate basically what temperature that it's at, and we know what the density of the two phases are. Right, so we fix the temperature, we fix the pressure, we have fixed all of the state of the system. But the question we have to ask ourselves is that the right pressure? How do we know that we have drawn that pressure line at exactly the right conditions, that we've matched our vapor pressure perfectly? And we're going to check with using this equation at the bottom. So I'll try and use different colors to highlight this. The first step in performing this integration is we're going to break it down and go from P alpha to PA of V dP. Okay, so we're starting here, and we are integrating down to there. Now, the lower limit of the integral is greater than the upper limit of the integral, so this is a negative area. So we're going to end up subtracting it. This is this area here. Okay, so we're integrating along a path of constant temperature. The next step is we have to go from PA, where we last finished off, to PB of V dP. In this case, PA is lower than PB, so this is a positive area. Let's remember, if you switch the limits of an integral, you just minus it. So this area is this big block right here. So in this region over here, this little quadrant, right, we both have a positive area and a negative area, so boom, it's gone. Now the last step to finish it off is we have to go from PB back down to P alpha of V dP. So is this a positive area or a negative area? Negative. That's because the limits, the bottom one is bigger than the upper one. So it's actually a negative. This one corresponds to this region here. It's a little bit weird. It's turned sideways. But hopefully going back and reviewing the video, it's clear. It's a little busy right now. Okay. So what we're left with is only this area, I'll call area 1. Right, all the other ones canceled out. And this area, which I'll call area 2. So if area 1 is equal to area 2, we have satisfied the requirement that delta G is equal to 0. And that we have perfectly selected the right pressure. So, if you were to take an equation of state off the shelf, there's a couple of things that need to happen in order for you to accurately predict vapor-liquid equilibrium. One, you have to be below the critical point. If you're above the critical point, you will not get this wobbly feature. You will only get one phase. You have to be in the two-phase region, right? Which means you have to have the curvature that's characteristic of a cubic function. The second thing you need to do is you need to guess a pressure. For every temperature isotherm that you draw, and we just drew one temperature isotherm here. For every temperature isotherm you draw, there will be exactly one pressure that accurately gives you the right value for the vapor pressure. And how we know it's the right value for the vapor pressure is because it demonstrates that these two areas cancel out, which corresponds to having the Gibbs free energy be constant across those two phases. But, and here's the kicker that we didn't talk about quite yet, before we can even attempt to do the area, we don't even know what these points are. That's because all of these equations of state are pressure explicit, which means that they're volume implicit. So if I write out the van der Waals equation of state, P is equal to RT over V minus B minus A over V squared. If I fix the temperature, or I want an isotherm, I can give you guys the pressure, and you should be able to solve for the volume. Or I give you guys the volume, you should be able to solve for the pressure. Clearly, one of those two is a lot easier than the other. If you know the volume, it's trivial to calculate the pressure, because the equation is explicit with respect to pressure. If I give you guys the pressure, that means you have to solve the cubic equation of state just to know what are the possible options of the density of the two phases. So I'm telling you all this is because you will have to do this for homework too. You will have to calculate the vapor pressure of a fluid using a cubic equation of state. I think that's usually what I do on homework 2. Then on homework 3, I make you guys calculate the vapor pressure of a fluid all the way up to its critical point, and calculate its delta H of vaporization, and calculate its delta S of vaporization, and compare it to experimental measurements. So you have to start to learn how to code this up to do it normally. Because on the first time, you could probably just sort of guess and check and then make sure that the areas cancel out. But when you have to calculate the vapor pressure 50 times, going from 0 to 600 degrees Celsius, for example, if you're doing the phase diagram of water, sorry, 600 Kelvin, I think, right? You're going to have an automated way of doing this. So when you're using this approach to do phase equilibrium with a cubic equation of state, you draw some isotherm, right? We've drawn the isotherm here at some temperature. Then you have to guess a pressure that you think is probably the vapor pressure. You draw a line. That's your best guess of what the vapor pressure is. Then you have to solve the equation of state to know what are these endpoints here. You have to know what the density of the fluid is. Then you have to compute the areas. And if you got lucky, you're done. But if not, you have to do another guess, try it again until you get it right. So these guess and check themes are basically what nonlinear solvers are designed to do. So in a computer program like MATLAB, it will do a guess and check. It doesn't care what's going on in the inner workings. It'll just keep on grinding away until it satisfies those conditions. This is sort of a tedious and cumbersome process. So instead, fugacity was invented to help us solve these problems, to make the process a little bit more streamlined. So instead of having to do this iterative procedure where we're trying to match areas, you can instead just match the fugacities, and we'll have a uniform, nice, consistent way to calculate the fugacities. So that's where the whole concept of fugacity comes into. But this is non-trivial. Right? This is where you got to do a lot of calculations just for something that seems like a relatively straightforward concept, the vapor pressure. Yeah, question?
One more question. You want to use fugacity or just like write a program that says hey, if this is, over this amount, then I want you to, change the vapor pressure to this, and then say, you overshoot, then,
I'll let you do whatever you want. So you can do it using areas. The reason why fugacity is so nice is because you can analytically derive an expression for the fugacity of a van der Waals fluid, for example. And then you have an analytical expression that you can just plug the numbers into reliably. Or you can go about and you can analytically derive an expression for the fugacity of a Peng-Robinson fluid or an SRK fluid. That's what makes the fugacity so convenient, is you can pre-calculate all of your work so that when you go and implement this into an actual phase equilibrium solver, you can just basically, I'll grab the fugacity for van der Waals off the shelf, or I'll grab the fugacity for the Peng-Robinson off the shelf. And so on Monday, we're going to talk about what is the definition of fugacity and how do we use it. Okay, we're out of time. So have a good weekend, and see you on Monday.